Well, today we're going to look at the next section. Well, I was actually planning on getting into or touching base on this last time, but well, it looks like some exercises took a good minute to go through. And well, so the cross product is another vector multiplication. So recall that there's two ways to multiply vectors. That's the dot product, and in this case, the cross product. The dot product. It's a multiplication whose result is another number. And we define that as how much more powerful the original vector is when multiplied by a second vector. Okay, and we use it to find projections and some applications in physics. For the cross product, we're going to multiply the vector to obtain a new vector, not a scalar. And well, but before looking at the cross product, we need some review here, some prerequisites. That in this case, to evaluate a determinant, and in particular 2x2 determinants and 3x3 determinants. Typically, this is covered in a pre-calculus course or in college algebra, course, and we're going to need this for finding cross products. Well, so the determinants of a 2x2 matrix, those are relatively easy to compute. All we do is find the product of the elements on the main diagonal, A times D, and subtract by the product of the elements in the secondary diagonal. However, the determinant of a 3x3 matrix may not be that as quick as the 2x2. And well, actually, I'm going to show you how do we compute using this method I have here, but then I'm going to give you a shortcut that only works for the 3x3 and in this case you can use either way. Okay, how it works, I'm going to show you this in the example that we have here. So let's look at a couple of examples. We have the determinant on letter A. Let's multiply the elements along the main diagonal. That's 4 times 1, and subtract the product of the elements along the secondary diagonal. Okay, so that's 4 times 1, which is 4, minus actually plus 6, and that equals to 10. All right, so that's the determinant of this 2x2 matrix. Very simple multiplication here. Now for a 3x3 matrix, and by the way, the determinant can only be found on matrices that are square matrices like 2x2, 3x3, 4x4. I don't know if some of you are in linear algebra. I don't think you have gotten to this chapter on determinant yet, but eventually you're gonna get there. But don't worry. This class doesn't expect you to know anything from linear algebra. I'm just going to mention the connections. Okay, so to compute the determinant of a 3x3 matrix, we do it by means of expansion by minors. Well, what do we mean by expansion by minors? And in this case, we can expand determinant on a preferred row or a preferred column. So typically, for the sake of simplicity, we always expand along the first row because it's the first and it's a row, I guess. And every element has a related sign, has an associated sign. We always start with a plus, minus, plus, and that's if we were to expand along the first row. If we were to expand along the second row, well, we continue on the next sign. So here we had a plus, then we go minus, plus, minus. All signs alternate here. The next would be plus, minus, and plus. You can think of this as a checkboard of signs, if you will. All right? So in this case, we will expand along the first row. Well, to expand along the first row, let me go back with the formula here. So what we do first is, okay, I'm going to highlight the first row and the first column. Do you see the element that is common to the first row in the first column? Isn't it the number 2? Okay, that number 2 is called cofactor. Whoops. It's the cofactor related to that minor. And then, so the cofactor is 2, and the minor, which is a matrix that is one dimension less, is going to be a 2 by 2, is made by these elements that we are not highlighting. In this case, 7, 0, -2, and 5. All right. Let's do the same with, okay, first row, but in this case, second column. Number 1, the element that they have in common is -3, and the minor will be formed by the elements that we are not highlighting in this case. That is 3, 4, and -2, 5. But in this case, be careful because we have a negative sign associated with that second term. And plus for the third term, let me do it here. We can do the following. We can do the same. So which element do they have in common? The first row and the third column, isn't it the number 1? So that's 1 times, and the minor is 3, 7, 4, 0. Okay? And well, so what do we have to do in this case? We have to simplify 1, 2, 3 2 by 2 matrices in the same way that we did here. So let's go ahead and do that. So that's going to be 2 times 7 times 5, which is 35, minus 2 times 0, well, that's a 0, minus, that's a plus, and that's a 3 times 3 times 5, which is 15. And be careful here because 2 times 4, that's 8, but minus -8, that's positive 8. And 1 times 3 times 0, which is 0, minus 28. And after simplifying all this, the final answer has to be 111. Okay? All right. So as you can see, it's a little time consuming to do this expansion by minors. All right. I mean, I have to teach this method because it's part of our objectives, and it serves as a connection with linear algebra for those of you who are taking it. And well, in order to find the cross product of a vector, of two vectors rather, if we have vector u with its own components and vector v and its own components, well, we can define the cross product by knowing the magnitudes in a similar way that we define the dot product. But the dot product had a cosine. Remember, we saw that formula. We actually derived it, and we used it to find the angle between two vectors. So we have a second alternative to find the angle between two vectors, but instead of using the dot product, which is a lot shorter than the cross product, we use the cross product. But in fact, we're not going to use this formula. I'll let you know why. Or the second way, if we know the components of the vectors, and well, it's this big formula right here. You know, if you expand, we have I times u2 v2 u3 v3, and the same, right? It's kind of tedious to do that, but of course, I mean, if you have seen this before and you're already used to do it this way, you might have learned this topic in pre-calculus or trigonometry as well. Some courses teach it, some others don't. But I'm going to show you the shortcut to this, okay? So how about we look at one example and we find that cross product. All right. So, and then we're going to look at the properties and what the cross product mean. Okay. So, given the vectors u equals to I plus 3j minus 1k, or just minus k, and v equals 2j plus 5k, find the cross product. Well, Be careful when you see the vectors in linear as a linear combination of I, j, k, because in some cases, we like the second vector, we have only two terms, and we run the following risk of having 2, 5, 0, but this is not correct. Notice we have the components j and k, so my advice is to always rewrite them in component form. That's 2, 3, -1, and v equals, notice we don't have the I. That means the x component is 0, 2, and 5. Okay? So we are going to set up this, the cross product u crossed with v. And this is I, j, k. And we write the next row would be all the elements of the first vector. Actually, the order matters here. You'll see why. And then the third row will be the elements or the components of the second vector that we're multiplying. Okay? Well, what's the shortcut here? The shortcut, which only works for 3 by 3 determinants, is to repeat the first two columns. All right? And then from here, this is what we do. I'm going to multiply all the diagonals from left to right this way. I times 3 times 5. What do we get when we multiply those two? Isn't that 59? I times 3 times 5. And then the next product here, j times -1 times 0. Isn't that 0? Well, let me just write it as a 0j. And then the third product, k times 2 times 2, isn't that a 4k? And we're going to subtract and open parentheses, and then we're going to multiply the diagonals backwards, starting with the j times 2 times 5, isn't that 10j? And then I times -1 times -2, isn't that -2i? And last but not least, k times 3 times 0, well, that's going to be 0k. Isn't it a lot shorter? And then from here, let's just combine like terms, component by component. Okay, so 15i minus -2i, isn't that 17? 17i. What about the j? So 0j minus 10j, -10j. And last but not least, 4k minus 0k, that's plus 4k. All right, and that's our cross product. Okay. I mean, of course, if you feel comfortable doing the expansion by minors, that's fine. If that's something you learned before in pre-calculus or you've seen this before, but I can offer this. I can accept this as this shortcut as an alternative, especially on the exam we're gonna be doing a lot of cross products the entire semester. So I think the shortcut would be fine. Well, some properties of the cross product. Well, in this case, we have some essential differences between the dot product and the cross product. So when we multiplied two vectors using the dot product last time, it was the same whether we multiplied u times v or v times u. So in other words, the commutative property it applies in this case. However, that's not the case for the cross product. Multiplying the vectors in the opposite order changes the sign of the result. Okay, let me explain this why. So if you rewrite, for example, this matrix, instead multiply V cross with U and change I, J, K, and instead of U and then V, start with V. Essentially, what are we doing? We're interchanging two rows in the matrix. For those of you that are in linear algebra, you will see in determinants that when you interchange rows on a matrix, when computing a determinant, that changes the sign of the result. So that's another connection with linear. Right? So that's one of the reasons why that gives it the opposite. And then the geometric interpretation will show the consistency of this result. For number 2, a number times a vector cross with another number times another vector, multiply the two coefficients, and then do the cross product. So the next property, it's basically the distributive property. So U cross V and U cross W plus U cross W. So that's and well, for number 4, well, what happens with that one? So as I said, that commutative property, it doesn't work in this case, but it only works when one of the vectors is the 0 vector, because in this case, if we find the determinant of a vector times the 0 vector, all zeros. Another property of determinants that you may have seen in pre-calculus and that you will see in linear algebra is that whenever you have a row or a column of all zeros, the determinant is 0. And in this case, the commutative property is fine. A vector times 0 is the same as 0 times the 0 vector, and then the 0 vector times another vector. And when we find the cross product of a vector and itself, we get the cross product. We get the 0 vector, and the result is, because that's another property of determinants, when you have two rows being the same, like in this case, the determinant is also 0. Okay? And then we're going to get the 0 vector. Geometric properties of the cross product. Well, this is the key idea here. This is the reason why we need to pay special attention to this. This concept will be key for the rest of the semester. So we're multiplying a vector times another vector. The angle in between them doesn't matter. All right? So the result is another vector, but this vector happens to be orthogonal to both U and V, whatever that is. 90 degrees and another 90 degrees between them, right? So, and well, so the angle between two vectors, that, like I mentioned before, we have in a way an alternative to find the angle between two vectors. However, we're not going to use the sine function to find the vector, because we have a problem with that function. In the case that to find the angle between two vectors, we need to find the arcsine. And well, to find the angle using the cosine, that's using the dot product. So analyzing these two formulas, on the one hand, well, the denominators, well, take the magnitude of two vectors. Well, we already know how to calculate those. Don't take too long to calculate. But between a dot product and a cross product, it takes longer to find a cross product, even using the shortcut that I've just showed you. But that's not the problem. The issue is with the range of the inverse, or the domain of the inverse sine function. The inverse sine function, the arcsine function has a, is that a domain? No, it's not a range. The range is going to be negative pi over 2 to pi over 2. And as opposed to the arc cosine, goes from 0 to pi, to 180. And there is an issue with vectors having negative angles, right? And as we defined in the previous section, we were discussing that the angle between two vectors goes from 0 and 180 degrees, right? I mean, even if you have these two vectors, okay, because these vectors will define physical and visible quantities, I mean, we're seeing a positive angle regardless of the orientation of the vectors, right? So that's why we have issues with these negative angles when it comes to vectors. So that's why we're not going to use the sign. We're going to use the one with the dot product, which is also a lot shorter. And another thing is that when we have two vectors that look different, for example, u and v, their cross product is going to be 0 if one of the vectors is a multiple of the other vector. And that's again because if we come back to the definition, for example, let's say this is 2 times 2 times 2 times, twice the vector. Well, essentially we can factor out a 2 and we still end up with 2 equal rows, giving us a determinant equal to 0. Some of the physical applications here. Actually, in this case, I forgot the absolute value bar. Well, it's not absolute value, it's the magnitude. The magnitude of the vector that we obtain will give us the area of the parallelogram spanned by these two vectors. For example, this area right here is the magnitude of that cross product. Okay? And well, we already saw that the product of the cross product of a vector with itself is the 0 vector. Okay, what happens with what about this right-hand rule? So this is very important when it comes to multiplying vectors. So suppose that I'm multiplying the two vectors, these two vectors like this. So the right-hand rule tells us that when I extend my hand and then I pull my fingers, check the direction of my thumb is going up. So when I multiply u times v, I have to get a vector in this direction. Otherwise, if I multiply them in the other direction, the orthogonal vector is the same but in the opposite, with the same magnitude but in the opposite direction. And this is going to be very, very key when we define the cross product of the unit vectors I and j, which is a very interesting pattern that you will see here. Alright, so find the cross product of the unit vectors I and j, where the vector I is the same as saying in component form 1, 0, 0, and the j vector is 0, 1, 0. So let's set up the determinant to find the cross product, and that's I cross with j. That's the determinant I, j, k, and that's a 1, 0, 0, 0, 0, 1. Oh, no, 0, 1, 0. And well, let's use the shortcut to multiply to find this cross product. And we do that by repeating the first two columns. And multiply the diagonal. So I times 0, well, that's going to be 0. J times 0, well, that's another 0. And K times 1, that's K. All right? And backwards, so first of all, minus J times 1 times 0 is 0. I times 0 times 1 is 0. K times 0 times 0, well, that's 0, so the cross product between I and J should be K. And well, we can see this geometrically. If we recall this picture from the last section, and well, let me label X, Y, and Z, the three. So I is a unit vector in the direction of X, right? And J it's a unit vector in the direction of Y. Okay. Get the markers again. So this is I, this is J. In accordance with the right-hand rule, we're doing I times J in this direction. Isn't it my thumb the K vector? All right. So now, what would be the cross product in the reverse order, J times I instead? Negative K. So it would go, well, thumbs down, right? So a pretty cool pattern here. I, J, and K. So when we multiply I times J, what do we get? K. If I multiply J times K, alright, if I multiply K times I, and that's the pattern when we go in circles. And when we go backwards, so K, okay, J times I, in the counterclockwise direction, we would be getting the opposite in sign of the vectors. Alright? So that's the geometric interpretation of the vector, of the cross product between two vectors. It's a new vector that is orthogonal to both vectors that we're multiplying, and it opens in the direction, well, based on the right-hand rule. All right? Okay, let's look at example number 4. Consider the vectors u2, 1, negative 3, and w, negative 1, 5, 3. Find a unit vector that is orthogonal perpendicular to both u and w. Okay, so another cross product. So u crossed with w. Let's set up I, J, and K. And that's a 2, 1, negative 3, negative 1, 5, 3. And let's repeat the first two columns. And multiply diagonals. Is that a 3 also? Doesn't look like a 3. So this will be I times 1 times 3, isn't that a 3I? And then J times negative 3 times negative 1, isn't that a plus 3K, or plus 3J rather? And K times 2 times 5, 10K. And then minus, open parentheses, because the sign will affect the results of multiplying the reverse diagonals. So that's J times 2 times 3, that's a 6J. And I times 3 times 5, which is 15I, but because of the negative, that's a negative 15I. And last but not least, K times 1 times negative 1, isn't that negative K? And let's just combine like terms. So i's with i's, that's 3. Okay, negative negative becomes positive, isn't that an 18i? J, so 3 minus 6, that's a negative 3j. And 11 minus negative k, that's plus k, 11k. Okay? Yes?
So, I remember how in the first method where we split it up into separate ones, we would make the j negative. We don't account for that one.
No, we don't. So we add the products from left to right, the ones I did in purple, and we subtract the products I did in green. But we don't do the plus minus alternating part in like we did in the splitting by minors. So that's the vector. However, they're asking us to find a unit vector. Well, let's call this vector v. Okay, for now let's call it v. But they're asking us to find a unit vector. How do we find a unit vector? Divide by the magnitude. So let's find the magnitude of v. That's the square root of 18 squared plus a negative 3 squared plus 11 squared. And the magnitude of this vector equals to the square root of 454. I want to make a comment about the results that we would be getting. MyMathLab might ask you to reduce these radicals, try to factor like a perfect square or anything. But on the exam or something, if you get numbers like this, no need to simplify those. Unless if they're numbers like the square root of 8, the square root of 12, which are easier to factor, well, those I would ask you to simplify. But something like this, just leave it like this, okay? So to get a unit vector in the direction of v, so that's v with a hat, that's how we denote a unit vector. It's going to be the vector v divided by its magnitude. And in this case, well, just write down the vector. I'm going to write it in component form just to make something different. And divide by the magnitude, which is the square root of 454. And actually, on the exam, an answer like this is fine. No need to distribute for every component. On the homework, however, it may ask you to distribute for every single term. All right, letter B. For part B, they're asking us to find the area of the parallelogram with U and W as adjacent sides. So coming back to the previous page, the area of the parallelogram is found by finding the magnitude of the vector that is obtained when doing this cross product, right? But didn't we do it already?
Yeah.
I think we got that result from here. All right, area, which is the magnitude of the vectors u crossed and w. Well, we don't have to do this operation again. Just use the result from before, and that's the square root of 454. Okay. Find the angle between the vectors. Well, so again, we already discussed this, and instead of using the cross product formula involving the sine function, we're still going to stick to the cosine function because of the restrictions on its range. The inverse cosine function outputs values from 0 to 180, which is the requirement between the angle between two vectors, not negative angles between negative 90 and 90 degrees, which the sine does. So in this case, let's go back to the cosine theta equals the dot product divided by the product of their magnitudes. And well, let's find the dot product of these two vectors. So Okay, let me write the vectors again so I don't scroll up and down. U, which equals 2, 1, negative 3. And V, which equals negative 1, 5, 3. And well, the dot product U dotted with V, it's the sum of the product of each corresponding component. So that's 2 times negative 1, which is negative 2, plus 1 times 5, which is 5, minus 3 times 3, which is 9. And that's going to be, is that a 6? Negative 6? And we also need the magnitudes of each vectors, which we don't have. So let's find them. The magnitude of the vector u, which is the square root of the sum of the squares of the components. So that's 2 squared plus 1 squared plus negative 3 squared. And that equals to the square root of 14. And then the magnitude of the vector w is the square root of, that's a negative 1 squared plus 5 squared plus 3 squared. That should give us the square root of 35. Okay. So let's put all this information in the formula here. In the numerator, let's write down the dot product, which is negative 6, over the product of the magnitudes, which we got in the bottom part. So that's the square root of 14 times the square root of 35. However, let me rewrite the expression over here because I need to set it like an equation. That's cosine theta equals negative 6 over square root of 14 times square root of 35. But to get the angle, we need to take the inverse cosine of this expression. And again, be careful to have your calculator in degree mode. Yes?
Sorry, just because you put under the U, you could be...
Oh, yes, should be W. Yeah, should be W. Thank you. And W, yeah, everything else. Thank you. So that's a negative 6 over root of 14, root of 35. And theta should be about 105.7 degrees. All right. Questions about anything so far? Yes?
So when you use the thumb rule for these two vectors, will it be going down or up?
We would be, we would need to graph those vectors to see their directions, So in this case, well, we're just going with the numbers because it's hard to plot stuff in 3D. When we did plotting points, it was kind of hard just because of the perspective. So we just take the result in this case. The next exercise is to find the area of a triangle, and the triangle has those 3 vertices. Well, so we have the vertices A, B. Well, let me do B in this direction, and C. All right. And we are going to suppose these 3 points are in space, all right? And well, I really don't know the orientation of these 3 points because, coming back to the comments before, it's kind of hard to see the perspective when plotting points in 3D. But well, so here, this is the plan. So what we're going to do here is, find the area of this triangle. But well, the area of the triangle, isn't it half of the area of a rectangle? All right. And well, if we extend this triangle, this forms a rectangle. So we can find the area of this rectangle and divide it by 2. But now we need 2 vectors in this case, so we can find the cross product find the magnitude of the cross product, which will give us the area, and then divide by 2. We don't have two vectors, but we have information to define two vectors. In this case, we can define vectors A to B, and we'll recall that to find the vector defined by 2 points, we subtract terminal point minus initial point. In this case, because the arrow tells us that the direction the vector is going to, so in this case we're going to go 0 minus 2, 3 minus 4, and 1 minus 1. That's going to give us the vector negative 2, 3 minus 4 is negative 1, and 1 minus 1 is 0. So that's the first vector. All right. And then the second vector, it's going to be defined from A to C. All right. A, C. And subtract component by component. C is the terminal point. A is again the initial point. 2 minus 2, that's a 0. 0 minus 4, negative 4. And 5 minus 1, that's a 4. Is this the only way to solve the problem? No. You could have defined otherwise the vectors C to A and C to B, or B to A and B to C. Either way, since this is all about the same 3 points, you should get the same answer either way. All right? So let's see. Let's find the cross product between AB and not this absolute value bar, nope, because that's not magnitude. I'm only finding first the cross product. So that's I, J, K. And well, in the correct order, write down the next two rows as the components of each vector. Negative 2, negative 1, 0, 0, negative 4, 4. All right. So that's how we set up this cross product. And well, for the sake of time, well, we already did a couple of cross products. I will just give you the answer to this. You should get negative 4i plus 8j and plus 8k. All right. Well, so that's the cross product of the vectors. That's the vector that is orthogonal to both AB and AC. Well, the magnitude of that new vector that we obtained is going to give us the area of the parallelogram spanned by those two vectors. So number one, area of parallelogram is going to be the magnitude of AB cross with AC. And that should be the square root of negative 4 squared plus 8 squared plus 8 squared. And in this case, this will be the square root of 144, which in this case reduces nicely to the number 12. Okay, but that's the area of the parallelogram. We want the area of the triangle, which in this case is perfectly half of it. If we trace a diagonal, it's going to give us half of it. So area of the triangle ABC will be 1/2 the area, 1/2 of 12, which is 6. All right. Any questions about how we got any of the calculations, any of the results? Yes.
The cross product that we skipped, it would also have the ij extra.
Yes.
But repeated throughout.
Yeah, so if we were to do all the steps, yes. So I'm just giving the answer to save time. All right, so what else do we have? Applications of the cross product in physics. Torque, it's something that you have, for those of you who have taken a physics class. Well, torque is a twisting force that causes rotation. And one of the most common examples, when you are screwing or unscrewing a ball using a wrench, right? So you are applying a force onto the wrench to cause the rotation and eventually screw it or unscrew it depending on the purpose. Well, in this case we have the vector F, which represents the force in which this is being pushed, and the vector R, which is the direction of, in this case, the wrench that we use. So now let's think about it. Okay, so what if both of those two vectors, and by the way, this should be vectors right here. This should be bold case. Okay, let's think about it. What happens if the force using both forces, the one that we apply and the force on the wrench, they're both parallel? That is, R cross with F equal to, well, you can think of this, because both forces are parallel, and those two forces are vectors in the same direction. Essentially, you're pulling the wrench, right? What's going to happen? Nothing, right? There will be no torque, no rotation. All right, and now let's think about another pretty interesting, by the way, zero vector. Which direction would give the maximum torque? So how would you take advantage of the situation to get the most torque in this case?
90-degree angle.
90-degree angle. Okay, for example, let's see. Tau, which is the torque, that's the magnitude, that's the magnitude of its cross product. And one of the definitions of the cross product involved the sine function, right? Okay, so this magnitude is a maximum whenever the sine function is a maximum. Recall the graph of the sine function. Well, where do we see the maximum here? Isn't it 90 degrees? Well, that's the mathematical justification to the other way. It's like common sense. How do you screw or unscrew using a wrench? You don't do it diagonal in the diagonal. You do it actually perpendicular to the tool, right? So that's how you get the most force out of it. Okay, so but this is the math behind that situation. All right, so let's look at a couple of examples. Number one, we have R, which is the vector OP described by I plus 2J plus K, and a force of 10 of a vector in the direction 10, 5, 0. Well, in this case, we're not even going to care about the angle, but we will in the next example. So let's do one example in which they're asking us to find the torque about the point O which produced and find its magnitude. Okay, so tau, which is the cross product between R and F, that's the determinant I, J, and K, and that's a 1, 2, 1, that's the vector R, those are the components, and 10, 5, 0. Okay, so again, the trick here is to repeat the first two columns, but again, just to save time, I'll give you the result of this vector. Okay, so that should be the vector negative 5i plus 10j minus 15k. All right. But well, in this case, they're asking us to find the torque, and in this case, it's the magnitude, not just the torque vector, but rather its magnitude. I mean, so, and the magnitude of tau, that's the square root of -5 squared plus 10 squared minus, plus -15 squared. That's you. And this should give us the square root of 350. And one more example, well, one example in which we are given the vectors in magnitude form. In this case, I mean, we don't need to compute any single 3x3 determinant to solve this problem. So what do we have? A 30 Newton force applied on a wrench that is 20.25 meters long. Determine the magnitude of the torque when the force is applied at an angle of 60 degrees to the wrench. And like it was mentioned in this case, well, this is going to be, this is not the maximum torque because it's at an angle other than 90 degrees, right? So let's see. So the magnitude of tau, which is the magnitude of the cross product between R and F. And well, we can use the other definition, the magnitude of R times the magnitude of F times sine of the angle. And in this case, we're given these pieces of information in numbers. So the magnitude of R, that's the length of the wrench, that's 0.25 meters, and the force of 30 newtons, and sine of 60 degrees in this case. Calculator multiply, so that should give us 3.75 root of 3. And in this case, the units are newtons meter or joules. And this is final answer for this applied example.